Surely we have a responsibility to care for our blue planet. The future of humanity, and indeed all life on Earth, now depends on us. There was a time before everything we know. Before the first forest, before the first wave, before the first breath of any living thing, before the oceans had settled into their basins, and before the sky had learned the color blue. There was a time when the Earth existed in a state of pure, unwitnessed becoming. It turned in the darkness, shaped by forces older than itself, moving through a silence so complete that there were no ears anywhere in the universe to hear it. This is that time. It belongs to no creature. It was witnessed by nothing. It unfolded according to rules older than the planet, older than the sun, older than the particular arrangement of stars visible from this small corner of the galaxy. It was not a story being told to anyone. It was simply a process, vast and patient, proceeding at its own pace across timescales the human mind was never designed to hold. And yet, here it is, written into the rock beneath your feet, preserved in the chemistry of the air you breathe, folded into the slow turning of the planet itself, which still carries in its molten heart the memory of its own birth. The story of the Earth before life is not a violent story, though it contains violence. It is not a lonely story, though it contains solitude. It is, above all else, a quiet story, a story of matter finding its way, of gravity doing its patient work, of heat slowly surrendering to the cold of space over timescales, so long they become, in their own way, restful. Close your eyes, if you like. The Earth does not need to be seen to be understood. It has been turning in the dark for a very long time. Part 1. Before the beginning. The universe was already old when the Earth was born. Not old in the way a mountain is old, or old in the way a civilization measures its years. Old in the way that makes all other ages feel like an afternoon. The universe had been expanding for 9 billion years before a particular cloud of gas and dust, drifting quietly in one of its unremarkable spiral arms, began to collapse. That cloud was not special. There were others like it, scattered across the galaxy, each one a slow accumulation of material shed by older stars. Each one a library of elements forged in nuclear fires that had burned and died long before. The atoms in that cloud had histories. Carbon born in the cores of red giants. Iron hammered into existence in the final moments of supernovae. Hydrogen, ancient as the universe itself, left over from the first minutes after the beginning. For millions of years, the cloud drifted. It absorbed the faint light of distant stars. It slowly grew colder at its edges, while its center remained warmer. Gravity worked on it the way gravity always works, quietly, without urgency, pulling matter toward matter with a patience that has no comparison in human experience. Then, something disturbed it. Perhaps a nearby star exploded. Perhaps a ripple passed through the galactic arm, a wave of density created by the slow rotation of the Milky Way itself. Whatever the cause, the cloud began to contract. Its outer edges began to fall inward. Slowly at first, then faster, as the growing mass at the center pulled with increasing force. The collapse took tens of millions of years. As the center compressed, it grew hotter. The atoms falling inward collided with one another, and their energy had nowhere to go but into heat. The core of the collapsing cloud became a growing sphere of hot gas, slowly accumulating mass, slowly brightening. Around it, the remaining material that had not yet fallen to the center began to spin, flattened by its own rotation, into a disk. Within that disk, the same process repeated on a smaller scale. Dust and ice clumped together, pulled into aggregates by electrostatic forces and by gravity. Small clumps became larger ones. Larger ones became boulders. Boulders became planetesimals, bodies large enough to exert meaningful gravitational pull on everything around them. The disk was full of collisions, not violent, explosive impacts, but slow, grinding encounters between objects moving at similar speeds, bumping and merging, building mass over millions of years of patient accumulation. The process is called accretion. It sounds gentle, almost domestic, and in some ways it was. The solar system assembled itself the way sediment builds on a riverbed, one layer at a time, each addition so small as to be individually unremarkable. At the center of all of this, the young sun ignited. Hydrogen fusion began in its core, and for the first time in this corner of space there was light. That light swept outward through the disk, heating everything it touched. Closer to the sun, the lighter, more volatile materials, water ice, methane, ammonia, were pushed outward by the solar wind. Only the denser, rockier materials could withstand the heat and remain in the inner disk. This is why the inner planets are rocky and the outer planets are giants of gas and ice. The sun sorted its own material as it was born, pushing the light things away and leaving the heavy things behind. In the inner disk, a small region began to dominate. One planetesimal among many had grown large enough to pull everything near it into collision with itself. Each impact added mass, and with mass came gravity, and with gravity came more impacts. The process accelerated. What had been a slow accumulation became something faster, more pronounced. The growing body swept its orbital neighborhood, gathering rock and metal and the occasional icy body that strayed in from the outer disk. In tens of millions of years, it had grown to the size of a small planet. This was the proto-Earth. It did not yet have a moon. It did not yet have stable oceans. Its surface was not solid in any meaningful sense. It was a sphere of hot rock and metal, partially molten, bombarded from all sides by the remaining debris of the disk. But it was there, and it was growing, and it had begun the long, patient process of becoming the world we know. Part 2. The Molten World. In those first millions of years, the Earth was not a place in any sense we would recognize. The surface was liquid, not liquid like water with its coolness and its transparency and its gentle yielding. Liquid like molten basalt, orange and black, thick and slow-moving, radiating heat into the surrounding void. The ground, if you could have stood on it, which you could not, would have been a gently undulating surface of cooling rock, constantly fractured from below by the heat pushing upward. There was no sky, or rather there was an atmosphere of sorts, but it bore no resemblance to air. It was a dense envelope of vaporized rock and metal, steam driven from the molten surface below, carbon dioxide belched from the interior, sulfur compounds swirling in thick yellow clouds. The young sun's light, already weakened by distance, filtered through this envelope and turned the world a dim, permanent amber. There was no blue, there was no green. There was only the color of hot rock and poisoned air. The planet was still growing. Even as its interior differentiated, with heavy iron and nickel sinking toward the center and lighter silicate rock rising toward the surface, impacts continued. Other bodies, the last remnants of the inner disk, still crossed the young Earth's path. Some were small, no larger than a house. Others were vast, the size of small moons, capable of shattering the thin, cooling crust and reopening the molten interior. Each impact released energy, and that energy became heat, and that heat kept the surface from ever fully solidifying. The planet turned quickly in those days. A day on the early Earth lasted perhaps 6 hours. The axis of rotation was different, the tilt uncertain. The planet spun through its orbit with a restless, rapid motion, quite unlike the stately pace it keeps today. No wind moved across the surface in the way we understand wind. There was pressure differential, currents of superheated gas moving above the molten rock, carrying sulfur compounds from one region to another. But there was nothing like breath, nothing like a breeze. Only the slow, thermal circulation of a poisonous atmosphere above a sea of liquid stone. Time passed differently here. Not because time itself moved at a different rate, but because there was nothing to mark its passage, no seasons, because there were no cycles of growth and dormancy, no tides, because there were no oceans. No days as we experience them, with their gradual brightening and darkening and the gentle rhythm of light and shadow. There was only the slow rotation of a hot sphere in space, and the gradual, almost imperceptible cooling that occurred at its surface when it faced away from the sun. Beneath the crust, if such a word can be used for something that fractured and remelted on a daily basis, differentiation continued. The iron core grew. As heavy elements sank and concentrated at the center, the core became more defined, more distinct from the mantle above it. The rotation of the planet, combined with the electrical conductivity of this molten iron, began to generate something invisible but consequential: a magnetic field. Weak at first, uncertain, flickering through configurations that would not have sustained life even if life had existed to sustain, but present. The magnetic field would become one of the great unsung protections of the planet's future. Without it, the solar wind, the constant outpouring of charged particles from the young sun, would have stripped the atmosphere away. The same thing happened to Mars, a world that lost its magnetic field early and was subsequently scarred bare by solar radiation. But on Earth, the iron core kept turning, kept generating that quiet electromagnetic cocoon, and the atmosphere, whatever it was, stayed. From space, in those early days, the Earth would have appeared as a dim orange sphere, glowing faintly from its own internal heat, wrapped in brown and yellow clouds, orbiting a young and violent sun. It had no beauty that we would recognize. It had no features we could name, no continents, no coastlines, no poles of ice. Just a molten sphere finding its internal organization, settling into its own structure with the slow gravity of an object that has all the time in the universe. And in a sense, it did. Part 3. The Great Impact. There is no gentleness in the story of the Moon's birth. Roughly 45 million years after the Earth formed, when the planet had achieved something close to its current mass, when the crust was beginning tentatively to show signs of cooling at its surface, something struck it. Not a small thing, not an asteroid or a comet, a planet, a fully formed planetary body roughly the size of Mars, traveling at a velocity that compressed time into a single, unimaginable moment. It struck the young Earth at an angle, not head-on, which would have shattered both worlds, but obliquely, a glancing blow of such force that the two objects partially merged, partially exploded outward, their crusts and mantles thrown into space in a spray of vaporized rock that encircled the Earth in a ring of debris. The impacting body had a name given to it long after the fact by scientists who traced its existence backward through the chemistry of the moon rock brought home by astronauts. They called it Theia. Theia no longer exists as a separate body. Most of it merged with the Earth, adding mass and heat and changing the composition of the young planet's mantle. Its iron core may have sunk to join Earth's own core, enriching the molten interior. The rest, the lighter mantle material, the silicate rock that made up Theia's outer layers, was thrown into a cloud of vapor and molten droplets that circled the Earth in a ring. That ring did not last long. Within a few hundred years, perhaps less, the debris began to coalesce. Gravity pulled the droplets together, and the same process of accretion that had built the Earth itself now built something new. A smaller body formed within the ring, growing rapidly as material fell into it from the surrounding cloud. In a geological blink, a new sphere had taken shape. The Moon. It sat much closer to the Earth in those early days than it does now. Perhaps 20 times closer, its face looming enormous in the amber sky, its surface still glowing from the heat of its own violent formation. The tidal forces between the two bodies were immense. They slowed the Earth's rotation, stretching those 6-hour days gradually longer, and they gradually pushed the Moon farther away, its orbit expanding incrementally over billions of years to the distance we observe today. The Earth, after the great impact, was, if anything, more extreme than before. The energy of the collision had remelted much of the crust, resetting whatever cooling had been achieved. The atmosphere, already thick and toxic, was enriched further by vaporized rock that had briefly escaped into space and then rained back down. The surface glowed again. The molten sea returned. And yet, something had changed. The planet was now more massive. Its iron core was larger, its magnetic field would become stronger. And in orbit above it, the new Moon would provide a stabilizing influence on the planet's axial tilt, preventing the wild wobbles that might have made the future development of stable climates impossible. The Moon, born of catastrophe, would become a steady companion. The story of the Earth is full of these exchanges. Violence that creates order, destruction that enables what could not otherwise exist. The impact of Theia is perhaps the most dramatic example, but it is not the only one. The whole history of the planet proceeds this way, through upheaval towards stability, through chaos towards something quieter and more sustaining. After the great impact, the long cooling continued. The Earth had reset itself, in a sense. The clock had not restarted, but the conditions had returned to an earlier state, and the planet had to find its way again through the same patient processes of differentiation and surface hardening that had been underway before. It would take millions more years. Part 4. The cooling. There is a particular quality to cooling. Not the dramatic cold of a sudden freeze, but the long, gradual cooling of something that holds enormous heat and releases it slowly, reluctantly, into the surrounding darkness. A blacksmith's iron held in open air, a stone pulled from a fire and left on bare ground. The principle is the same, only the scale is different. And on the scale of a planet, the process takes not minutes, but tens of millions of years. The early Earth lost its heat through radiation. The surface, when it hardened briefly, radiated infrared energy into space, losing heat with each passing night on the slowly rotating planet. But the atmosphere was thick and heavy with carbon dioxide and water vapor, and these gases trapped much of that radiation, slowing the cooling, keeping the surface warmer than it would otherwise have been. This was not yet the subtle, balanced greenhouse effect that would one day regulate the climate of a living world. It was a crude, oppressive blanket of gas, holding in far too much heat, keeping the surface of the planet closer to molten than to solid. The cooling was not smooth. Each time the surface began to harden, the interior pushed back. Volcanic outgassing released new heat and new gases. Impacts from the ongoing bombardment of the solar system's debris added energy that remelted the crust. The thin skin of cooling rock that formed at the surface was fractured, reabsorbed, and replaced over and over again in a cycle that was not interrupted so much as gradually wound down. The bombardment slowed, not all at once, but perceptibly, over millions of years. The solar system was running out of loose debris. The planets had swept their orbital neighborhoods relatively clean. The remaining asteroids and comets had settled into more stable orbits or been captured by the gravity of the outer planets. The frequency of large impacts on the Earth declined, and with fewer impacts came fewer remelting events. And with fewer remelting events came a longer period of time between each one, and in those longer periods, the cooling could proceed further than before. Patches of solid rock began to persist. They were dark, glassy, basaltic, formed from the rapid cooling of lava at the surface. They cracked easily under the thermal stress of the still hot interior. They were thin, perhaps only a few kilometers deep, before giving way to the partially molten rock below. But they were solid. They were something you could, in theory, have stood upon for a moment, before the heat conducted through your boots and the poisonous air worked its way into your lungs. The first solid rock on Earth formed in this way, not dramatically, not with any ceremony, but as a simple consequence of physics. Material that is hot and loses heat becomes less hot. Material that is less hot becomes solid. The surface of the Earth became solid because the universe continued to follow its own rules, and those rules, given enough time, produce rock from magma. The sky above this solidifying surface was still opaque. Cloud cover, thick and unbroken, wrapped the entire planet. Not the soft white clouds of a temperate sky, but dense, dark layers of water vapor and sulfur dioxide and carbon dioxide, miles thick, blocking all direct sunlight. The surface existed in a permanent twilight, lit from below by its own glow and from above by the diffuse light that filtered through the cloud deck. Rain had not yet fallen. The water vapor in the atmosphere was too warm to condense into droplets large enough to fall. The planet existed in a state of perpetual steam, the hydrological cycle not yet triggered, the water locked in the air as invisible vapor, waiting for the temperature to drop far enough to release it. That moment was approaching. As the solid crust grew thicker and the volcanic outgassing gradually declined, the surface temperature began, very slowly, to approach the point at which liquid water could exist. The clouds grew denser as more vapor condensed in the upper atmosphere. And then, somewhere, at some moment too ancient to pinpoint, the first raindrop fell. It evaporated before it reached the ground. The surface was still too hot. The drop fell through thousands of meters of hot air and turned back into vapor before it reached the rock below. But it had condensed. The cycle had been primed. Above the surface, in the cooler upper atmosphere, water was beginning to gather into droplets, into clouds that carried more and more moisture, into weather systems that circled the globe on thermal currents. The rain came in earnest when the surface had cooled enough to let it land. It did not come gently. It came in torrents, in deluges of hot water falling from a sky that had been holding its breath for millions of years. The drops hit the rock and hissed, and some evaporated immediately, but some stayed, collecting in the low points of the uneven surface, forming the first puddles, the first pools, the very first standing water on the face of the earth. Those pools were not clear. They were grey with dissolved minerals, acidic from the carbon dioxide that had dissolved into the falling rain, warm from the heat they absorbed from the ground below. They were not beautiful in any way that the word is usually used, but they were water. And water, once established on a surface, begins to do things. It dissolves rock. It carries minerals. It seeks its own level, flowing downhill, pooling in basins, connecting with other pools through tiny channels worn into the basalt. The hydrological cycle had begun. Rain fell, collected, evaporated from the warm surface, rose into the atmosphere, condensed, and fell again. Over millions of years, this cycle did two things simultaneously. It slowly filled the low-lying basins of the planet with water, building toward the first oceans. And it slowly drew carbon dioxide out of the atmosphere, dissolving it into the rainwater and depositing it in chemical compounds on the sea floor. As the carbon dioxide declined, the greenhouse effect weakened. The atmosphere became slightly less opaque. The surface cooled a little faster. The rain fell a little colder. The oceans deepened a little more. Each change fed the next. The planet was finding, slowly, a new equilibrium. Part 5. The ocean forms. Water covered more of the Earth's surface in those early days than it does now. There were no continents to speak of. The crust was thin and roughly uniform, basaltic, dark, not yet differentiated into the lighter granitic rock that would eventually rise above sea level and form the permanent landmasses of the later Earth. The basins filled, and what little solid ground existed above the waterline was small, irregular, and constantly reshaped by the volcanic activity that still ran beneath the crust like veins of fire. The ocean was not blue. It was not the deep, clear, sunlit blue of a tropical sea on a modern afternoon. It was dark, tinted green by dissolved iron compounds and the mineral richness of the water. It was warm, heated from below by the volcanic heat that had not yet retreated far enough from the surface. And it was acid. The water that filled the early ocean basins had fallen as rain through an atmosphere rich in carbon dioxide and sulfur dioxide, and both of those gases dissolved easily into water to form acids. The pH of the early ocean was well below 7, the neutral point that marks the boundary between acid and alkaline. This acidic ocean would have dissolved many of the minerals we associate with modern seawater, and it created a chemical environment quite unlike anything that exists on Earth today. Yet even this harsh chemistry had a purpose, in the sense that all geological processes have purpose, which is to say no purpose at all, but an outcome. The acid water dissolved the rock over which it moved, drawing calcium and magnesium and other elements into solution. It reacted with the basalt of the seafloor, exchanging one chemistry for another. Slowly, over millions of years, the composition of the ocean changed. The acid was neutralized, the minerals accumulated. The water became what chemists call a buffered solution, resistant to extreme swings in pH, more chemically stable than it had been. The ocean was learning chemistry. On the seafloor, in the darkness below the surface layer, something else was happening. Heat from the interior was still escaping, but now it had a new pathway. Water had percolated down through cracks in the basalt and encountered the hot rock below. The water heated rapidly, dissolved minerals from the surrounding rock, and then, driven by pressure, rose back toward the seafloor in plumes of superheated water. Hydrothermal vents. These vents would later become famous as the possible birthplace of life. But in the period before life, they were simply geological features, chimneys of hot, mineral-rich water rising from the seafloor into the cooler water above. They built structures around themselves as the minerals they carried precipitated out in the cooler water, forming columns and mounds of sulfide minerals. Some of these structures grew to considerable height, tens of meters above the seafloor, black and porous, riddled with tiny chambers and passages where warm water circulated in complex patterns. The chemicals that came out of these vents were not random. Hydrogen sulfide, methane, carbon dioxide, hydrogen gas, ammonia, metals in solution, iron and manganese and zinc and copper. These chemicals met the chemicals already present in the ocean water, and they reacted, not in ways that anyone guided, not in ways that produced any particular intended outcome, but in ways that generated chemical complexity that created new compounds not present in either the vent water or the ocean water alone. The ocean, in other words, was a chemistry laboratory. It had reagents, it had energy gradients, it had temperature differences between the warm vent water and the cold, deep ocean. And all of these things drove chemical reactions. But it had no experimenter. No one watched these reactions. No one recorded the results. The compounds that formed either persisted, if they were stable enough, or broke apart and their components rejoined the chemical soup. The ocean was doing what matter always does when energy is available and constraints are present. It was exploring the space of possible chemical arrangements, one reaction at a time, at a pace measured in millions of years. Above the ocean, the sky was clearing. Very slowly, the thick cloud cover that had wrapped the planet since its formation was thinning. As the carbon dioxide left the atmosphere, dissolved into rain and deposited on the seafloor, the density of the cloud layer decreased. Not overnight, not even over 1 million years. But over hundreds of millions of years, the sky above the early ocean became progressively less opaque. Sunlight, for the first time, began to reach the surface of the water. The sun at this time was younger and dimmer than it is today, producing roughly 70% of its current luminosity. By modern standards, this should have been enough to freeze the early ocean, because the carbon dioxide levels were not yet low enough to compensate. And yet, the ocean did not freeze. This paradox, called the faint young sun paradox by scientists who have puzzled over it, has not been entirely resolved. Perhaps the greenhouse effect of the remaining carbon dioxide was stronger than current models suggest. Perhaps methane played a larger role than previously thought. Perhaps the answer lies in something not yet understood about the early Earth's chemistry. What is known is that the ocean remained liquid. The surface of the water, wherever sunlight reached it, absorbed that energy. Photons struck water molecules and transferred their energy as heat, warming the surface layer. Temperature gradients formed, with warmer, lighter water floating above colder, denser water below. Currents began to move, driven by these temperature differences, by the Coriolis force of the rotating planet, by the winds that moved above the surface. The ocean was not still. It was never still. It moved in slow, vast patterns that crossed entire ocean basins, carrying warm water from the equatorial regions toward the poles and cold water from the depths up toward the surface. These patterns of circulation would become, over billions of years, one of the most important regulators of the planet's climate. But for now, they were simply the ocean moving, water finding its equilibrium. Warmth and cold exchanging positions in a slow, planetary scale dance that had no audience and no meaning beyond the physics that governed it. Part 6. The Hadean Night. The Hadean Aeon is named for Hades, the ancient Greek underworld. It is an apt name for a period that lasted roughly 500 million years, and was defined, more than anything else, by conditions hostile to the existence of anything we value. The Hadean Earth was not a place of suffering, because there was nothing to suffer. It was simply a place of process, of geology working through its early stages at the pace that geology requires, unmeasured and unwitnessed, indifferent to any quality we might wish to assign it. The Hadean Aeon is poorly preserved in the rock record. Almost nothing from this period survives as identifiable rock. The constant recycling of the crust, the bombardment from space, the volcanic activity that remade the surface over and over again, ensured that whatever rocks formed in the Hadean were almost entirely destroyed. The oldest rocks we have found from this period are tiny crystals of a mineral called zircon, found in ancient sedimentary formations in Australia. These crystals are approximately 4.4 billion years old. They are nearly as old as the Earth itself. Zircon is a remarkably durable mineral. It resists the same processes that destroy most other minerals: the heat, the pressure, the chemical attack of acidic water. These tiny crystals survived when everything around them was recycled and remade, preserved in later sediments like fragments of a letter written in a language that no longer exists. The chemistry of these ancient zircon crystals tells us something important about the world they formed in. They contain oxygen isotopes in ratios that suggest they crystallized in the presence of liquid water. At 4.4 billion years old, these crystals are evidence that the early ocean existed perhaps earlier than previously thought. That liquid water was already present on the surface of the Earth within 150 million years of the planet's formation. The Hadean Earth, in other words, was not quite as hellish as its name suggests. Or rather, it was hellish by any standard we might apply, but it was not uniformly hellish at all times. There were periods, perhaps relatively brief by geological standards, but long in absolute terms, when the surface had cooled enough for liquid water to exist, when the bombardment had paused long enough for the crust to thicken, when the clouds had thinned enough for sunlight to reach the ocean surface. These were not paradise. They were simply less extreme versions of an extreme world. Between these calmer intervals, the bombardment resumed. The late heavy bombardment, a period between approximately 4 billion and 3.8 billion years ago, saw a renewed influx of asteroids and comets striking the inner solar system. The evidence for this period comes partly from the lunar surface, whose ancient craters date predominantly from this time, and partly from the chemistry of ancient rocks that carry the signatures of impacts. The cause of the late heavy bombardment is still debated. One hypothesis suggests that a reorganization of the outer solar system as Jupiter and Saturn shifted their orbits slightly destabilized a reservoir of asteroids in the asteroid belt and sent a renewed wave of them into the inner solar system. Whatever the cause, the effect on Earth was significant. Impacts during this period were large enough and frequent enough to vaporize portions of the early ocean, sterilizing the surface in a way that would have prevented any life from taking hold, had life been present to sterilize. The ocean recovered. Each time an impact vaporized a portion of the ocean, the water vapor entered the atmosphere, and as conditions cooled, it fell back as rain and refilled the basin. The hydrological cycle was resilient in this way. Water, once established on the planet's surface, was remarkably difficult to permanently remove. It cycled through the atmosphere and back, distributed itself across the surface, and returned. The ocean, battered and temporarily diminished, endured. By the end of the Hadean, roughly 4 billion years ago, the worst was over. The bombardment was declining toward what would become its modern baseline rate of occasional random impacts rather than the sustained, frequent collisions of the early solar system. The crust had thickened enough to provide a more stable surface. The ocean had deepened. The atmosphere, while still toxic by modern standards, had become somewhat less extreme. The Earth was settling into its geology. Not into permanence, there would be no permanence for billions of years, but into a pattern, a rhythm of geological processes that would persist and evolve but not reset entirely again. Plate tectonics was beginning to organize itself. The interior heat that drove volcanic activity was establishing the convection patterns in the mantle that would eventually produce the movement of tectonic plates. The Hadean Eon was ending. What followed would come to be called the Archean, the Ancient Era, a period of nearly 2 billion years during which the Earth completed its basic geological organization and, eventually, produced the first life. But the Archean is a different chapter. The Hadean is the chapter of formation, of the most basic questions being answered, of matter becoming a planet and a planet becoming a world. It ends not with a dramatic event, but with a gradual quieting. The bombardment slows and does not restart at significant scale. The volcanic outgassing continues, but becomes less intense. The crust thickens and becomes more stable. The ocean deepens and covers more of the surface. The atmosphere, still lacking oxygen, still poisonous to anything that might one day breathe, becomes thicker, denser, more chemically complex. And above it all, turning in the darkness, the still young moon catches the light of the sun and reflects it down onto an ocean that has never held a fish, a shoreline that has never known a footprint, a sky that has never carried a bird. It is a quiet world. It has always been a quiet world in these earliest ages, before the chemistry grew complicated enough to matter. Part 7. The composition of the deep. Beneath the ocean, the mantle moved, not quickly. Nothing in the mantle moves quickly by any measure that would register on a human timescale. But on geological timescales, the mantle was in constant, slow circulation. The heat from the core and from the decay of radioactive elements within the mantle itself drove convection currents, giant loops of slowly flowing rock that rose near areas of intense heat and sank near areas of relative cooling. This convection is the engine of everything that happens at the surface. The movement of tectonic plates, the opening and closing of ocean basins, the formation and destruction of mountain ranges, the patterns of volcanic activity, all of it is driven by the slow circulation of the mantle, which is itself driven by the heat left over from the formation of the planet and the heat generated by the decay of radioactive elements. In the early Earth, this system was more intense than it is today. The planet was hotter, so the mantle flowed faster, relatively speaking. The crust was thinner, so it was more easily recycled. Volcanic activity was more widespread. The surface expression of all this internal activity was a world marked by frequent volcanism, by thin crust that cracked and shifted, by hydrothermal activity wherever the seafloor sat above regions of intense heat. The core of the Earth in this period was already established in its basic structure. At the very center, under pressures so extreme that the iron there is solid, despite temperatures above the melting point of iron at ordinary pressure, the inner core turned. Around it, the liquid outer core, a sea of molten iron and nickel thousands of kilometers deep, churned in complex patterns driven by the rotation of the planet and the heat escaping from the inner core. This churning generated the magnetic field that wrapped the planet. Not a simple uniform field like the field of a bar magnet, but a complex shifting thing, stronger near the poles, weaker near the equator, interrupted by local variations caused by the irregularities of the outer core's flow. It extended far into space, creating a region called the magnetosphere, a bubble of magnetic influence that deflected the solar wind around the planet, protecting the atmosphere from being stripped away. The solar wind was more intense in those days. The young sun was more active, producing more charged particles than it would in its later, quieter maturity. Without the magnetic field, the early atmosphere might well have been lost, as the atmosphere of Mars was eventually lost when that planet's magnetic field weakened and died. The fact of the Earth's magnetic field, maintained by the convection of its liquid iron outer core, is among the less celebrated but most consequential facts about the planet. It is the reason there is an atmosphere to breathe. It is the reason there is an ocean to sail. Without it, the story would have ended long before it began. The deep structure of the Earth in the Hadean and early Archean was not yet fully organized. The distinction between the upper and lower mantle, separated by a zone where the intense pressure causes minerals to transform into denser forms, was beginning to become pronounced. The crust was not yet divided into the thick, buoyant continental crust and the thinner, denser oceanic crust that characterize the modern Earth. That distinction would develop gradually as the planet's interior evolved. But the basic architecture was in place: core, mantle, crust. Heavy at the center, lighter toward the surface, hot below, cooling above, rigid at the surface, slowly flowing in the depths. The Earth had found its anatomy. Part 8. The first continent. Somewhere around 4 billion years ago, the first hints of continental crust began to appear. The process was not dramatic. It was a consequence of the same volcanic and tectonic activity that had been reshaping the surface since the planet formed. In certain places, where one piece of thin oceanic crust sank beneath another, at the boundaries where tectonic plates converged, the heat and pressure of subduction caused some of the material to melt and rise. This rising material was different from the dark basalt of the oceanic crust. It was lighter in color, lighter in density, richer in silica. Granitic rock, the material of continents. Where this lighter rock accumulated, it formed thicker sections of crust that sat higher on the mantle, their surface rising above sea level. Not mountains, not at first, just areas of thicker, lower density crust that stood slightly above the surrounding oceanic surface, exposed to the atmosphere, washed by waves, worn by rain. The first proto-continents were small, scattered across the surface of the planet like islands in a global ocean, constantly shifted by the underlying tectonic forces, occasionally assembled by those same forces into larger groupings before being separated again. They had no life on them, no soil in any meaningful sense, because soil requires the activity of organisms to form. Just bare rock, dark grey and brown, exposed to a sky still full of carbon dioxide and sulfur compounds, washed by acid rain, constantly eroded and redeposited into the surrounding ocean. On these bare rock surfaces, the first minerals experienced the chemistry of the open air. Minerals that had formed at depth under conditions of no oxygen and no water were now exposed to both. They reacted, they altered, they broke down into new mineral forms suited to the surface conditions. This process, weathering, would become one of the most important geological cycles on the planet, drawing carbon dioxide out of the atmosphere, locking it into rocks, and playing a crucial role in regulating the climate over geological timescales. On the bare rock, there was nothing else. No lichen creeping across the stone, no moss softening the edges of the boulders, no roots working their way into the cracks and deepening them. Just rock meeting air and water, pure chemistry, no biology. The weathering occurred at a rate governed only by temperature, rainfall, and the composition of the rock and the air. Rain fell on the bare proto-continents and ran off immediately, carrying dissolved minerals down to the sea. There was no soil to absorb it, no roots to slow it, no organisms to hold it in place. The runoff was rapid and mineral-rich, a constant delivery of elements from the land to the ocean that helped to make the ocean ever more chemically complex. The early atmosphere above these bare lands was changing slowly. Volcanic activity continued to add carbon dioxide and water vapor and sulfur dioxide to the air. But the weathering of rocks and the dissolution of carbon dioxide into the ocean were removing carbon dioxide as fast, or nearly as fast, as it was being added. A rough balance was being maintained. Not a perfect balance, not a deliberately regulated balance, but the kind of statistical balance that emerges from two processes working in opposite directions when the rates are roughly matched. The sky above the early continents would have been a dull orange-brown, the color of an atmosphere with high carbon dioxide and traces of sulfur compounds, without the oxygen that gives the modern sky its blue. Clouds moved across this sky, driven by the same thermal and pressure gradients that drive weather today, but with no land plants to moderate the temperature extremes, no forests to regulate water vapor. The weather was simpler, more purely physical. Wind blew dust from the bare rock surfaces, rain fell and ran off. The sun moved across the sky, its light falling on stone, on water, on nothing else. The planet was waiting, in the sense that all processes wait for their next stage, without awareness, without impatience, simply proceeding through each step as conditions allowed. Part 9. Deep Time and the Meaning of Stillness. There is a concept that geologists use when they want to convey the length of deep time, and it works like this. Imagine the entire history of the Earth compressed into a single year. The planet forms on the 1st of January. Life appears in early spring. Complex animals appear in mid-November. Dinosaurs go extinct on the 26th of December. And all of recorded human history, everything from the first cave paintings to the present moment, occurs in the last 14 seconds of New Year's Eve. On this scale, the period we have been describing, from the formation of the Earth to the end of the Hadean, occupies roughly the month of January. 500 million years of cooling, impacting, differentiating, ocean forming, crust building, and magnetic field generating, all occurring before any life existed, all occurring in geological darkness, in a world that held no memory of itself. It is difficult to hold this in mind without the mind finding ways to shorten it, to compress it, to make it feel like a sequence of events that followed one another with something like narrative pace. But the reality is different. Each million years of this period looked, in most ways, very much like the million years before it and the million years after it. The changes were cumulative and gradual. The ocean deepened by an amount too small to measure in a single century. The atmosphere lost carbon dioxide at a rate too slow to register in a single million years. The scale of these processes is its own kind of beauty, if you can step far enough back to see it. The same process that slowly dissolved carbon dioxide from the Hadean atmosphere also, billions of years later, played a role in creating the limestone cliffs of Dover, the coral reefs of the Pacific, the chalk soils that grow the wine grapes of Champagne. The chemistry that began in the acid ocean of the Hadean did not stop. It continued, adapted, incorporated into the metabolism of organisms, into the shells of invertebrates, into the bones of vertebrates. The planet's early chemistry is still with us. It never really ended. It just changed form. The silence of the pre-biological Earth is not an absence of process. It is an absence of noise. The geology was happening as it always had been. Heat was moving from the interior to the surface. Rock was forming and breaking down. Water was cycling through the atmosphere and the ocean. Minerals were dissolving and precipitating. Tectonic plates were beginning their slow journeys across the surface of the planet. All of this occurred without sound, or nearly so. The hiss of rain on rock, the deep subterranean groan of settling crust, the slow rumble of occasional impacts, growing rarer now, the wind across bare stone. These were the sounds of the pre-biological Earth, sounds no ear ever heard. Vibrations that moved through rock and water and air and then dissipated, absorbed back into the silence of a world that had not yet learned to make music of itself. There is something restful in this, not the restfulness of sleep, though perhaps something like it. The restfulness of a system that has not yet been complicated by life, by the extraordinary elaboration of chemistry that life represents, by the noise and metabolism and competition and cooperation that living organisms introduce into a landscape. The pre-biological Earth was simple, in the way that profound things are sometimes simple. Water, rock, air, heat. 4 things interacting according to physics and chemistry, producing over hundreds of millions of years a world of increasing complexity and subtlety. No drama, no urgency, no particular destination. Just the planet, turning in space, doing what matter does when it is organized into a planet and set in orbit around a star. Part 10. The slow architecture of the crust. Tectonic plates are, in a sense, the skin of a living planet. Not living in the biological sense, but living in the sense of being dynamic, responsive, in constant slow motion, driven by internal energy, always changing while always maintaining the basic pattern of its structure. The plates are the rigid outer layer of the Earth, the lithosphere, which consists of the crust and the uppermost part of the mantle. They float on the softer, more plastic rock of the asthenosphere below, carried along by the convection currents in the mantle, moving at speeds of a few centimeters per year. In the early Archean, the plate tectonic system was different from what it is today. The Earth's interior was hotter, the mantle more vigorously convecting, the crust thinner and more easily recycled. Some researchers believe that the modern style of plate tectonics, with distinct rigid plates separated by well-defined boundaries, did not fully develop until perhaps 2 to 3 billion years ago. Before that, the system may have operated differently, with smaller, more numerous plates, more rapid recycling of the crust, more widespread volcanic activity distributed across the surface rather than concentrated at specific boundaries. The transition between these two styles of tectonics was not abrupt. It was gradual, unfolding over hundreds of millions of years as the planet's interior slowly cooled and the dynamics of the mantle changed. What both styles had in common was the fundamental process of crustal recycling. At divergent boundaries, where plates moved apart, new crust was formed as magma rose to fill the gap. At convergent boundaries, where plates moved toward each other, one plate was pushed beneath the other in a process called subduction, the descending plate carrying material back into the mantle where it was remelted and eventually recycled into new crust. This cycle meant that the oceanic crust was never very old. The oldest oceanic crust on Earth today is only about 200 million years old, because anything older than that has been subducted and recycled. The continental crust, being lighter, was more resistant to subduction and therefore accumulated over time, growing older and thicker as new material was added at its edges. In the early Archean, the protocontinents were still small and scattered. They drifted across the surface, occasionally colliding with one another and merging, adding material along their edges from the volcanic activity associated with subduction. Mountain ranges formed where continents collided, though these were not the dramatic, sharp peaks we know from the modern world. They were gentler, rounder, more continuously eroded by the intense rainfall of a warm, humid world without much vegetation to hold the soil in place. The eroded material washed into the ocean and settled on the seafloor as sediment. Layer upon layer of sediment accumulated over millions of years, recording in its chemistry the conditions of the water and the air above it, the occasional impact of a meteorite, the episodes of volcanic activity that sent ash clouds across the ocean surface. These sedimentary layers are among the oldest rocks we have, and they are among the most informative. They tell us the pH of the ancient ocean. They tell us the composition of the ancient atmosphere. They tell us the temperature of the ancient sea floor. They tell us, in the chemistry of their minerals, something about the light that fell on the ancient sea surface, the currents that carried sediment from one region to another, the events that interrupted the slow rain of particles settling gently downward through the water column. These rocks are a memory. Not a memory in any conscious sense, but in the way that all records are memories, a preserved trace of what was available to be read if you know the language. The language here is mineralogy, geochemistry, isotope ratios, sedimentary structures. It is a language developed over 2 centuries of careful scientific observation, a language that allows us to read a 4-billion-year-old rock and know something about the world in which it formed. The crust of the early Earth was being written even as it was being built. Each new layer of sediment recorded something. Each new lava flow left its signature in the pattern of its minerals. The planet was, in a sense, keeping its own record, not intentionally, not for any purpose, but as a simple consequence of the fact that chemistry leaves traces, and traces can be read. Part 11. Water and the long patience of chemistry. Water is a strange molecule. By the rules of chemistry, it should be a gas at room temperature. Its close relatives, hydrogen sulfide and hydrogen selenide, are gases at ordinary temperatures and pressures. But water, despite being the smallest of the 3, is a liquid. The reason is the hydrogen bond. Each water molecule carries a slight electrical asymmetry, a concentration of negative charge at the oxygen end and positive charge at the hydrogen ends. And this asymmetry allows water molecules to attract one another. They form a loose, constantly shifting network of bonds, each one weak and fleeting, but collectively strong enough to keep water liquid at temperatures where similar molecules are gaseous. This physical property, this quirk of the electron distribution in a 3-atom molecule, is among the most consequential facts in the universe's history. Because water is liquid at the temperatures that prevail on the surface of the Earth, it can serve as a solvent. It dissolves more substances than almost any other liquid. It can carry minerals from rock to ocean, carbon dioxide from atmosphere to water, organic compounds from one location to another. It flows, fills, evaporates, condenses, and flows again, cycling through the hydrosphere in constant motion, always carrying things with it, always mixing, always reacting. On the early Earth, this chemistry was already underway, even in the absence of life. The ocean was a vast solution of minerals and gases, constantly stirred by currents and heated by volcanic vents, constantly receiving new inputs from the atmosphere above and the seafloor below. The chemistry that was occurring in this solution was complex, not as complex as the chemistry of life, but more complex than a simple mineral reaction. Carbon compounds were forming. Not the specific carbon compounds of life, not the precise molecules of proteins and nucleic acids, but simpler organic molecules, amino acids and sugars and fatty molecules that could form in the conditions present in the early ocean. This had been demonstrated by experiment. In the 1950s, a chemist named Stanley Miller took a flask of simple chemicals representing the early ocean and atmosphere, added an electrical discharge to simulate lightning, and let it run for a week. When he analyzed the result, he found that the flask had spontaneously generated amino acids, the building blocks of proteins. The experiment has been refined and repeated many times since, under conditions more accurately representing what we now know about the early ocean and atmosphere. The results are consistent. Simple chemistry given energy and time, spontaneously generates organic complexity. In the early ocean, this process had been running for hundreds of millions of years before life appeared. The ocean accumulated organic compounds, not in great quantities, diluted as they were through an immense volume of water, but persistently. In sheltered environments, in the porous rock of hydrothermal vents, in shallow tidal pools where evaporation concentrated the dissolved compounds, these organic molecules accumulated in higher densities. They reacted with one another. They formed more complex compounds from simpler ones. The ocean was, in this sense, slowly becoming ready for life. Not intentionally, not toward any end, but by the simple operation of chemistry over geological time, the conditions were assembling themselves. The components were gathering. But this is not a story about life. Life had not yet arrived. What we are describing here is the long preparation, the geological and chemical stage setting that preceded biology by hundreds of millions of years. The chemistry of the pre-biological ocean is interesting in its own right, not as a prelude to life, but as a demonstration of what matter does when you give it energy and time and a liquid medium in which to react. It becomes complex. Spontaneously, without direction, without goal, matter in solution generates increasing chemical complexity over time. This is not a mystery. It follows from thermodynamics. Energy flowing through a system drives it toward more complex states, and the flow of heat through the ocean, from the warm depths to the cool surface, from the volcanic vents to the surrounding water, was a continuous energy gradient that drove continuous chemical reaction. The ocean was doing chemistry. It had been doing chemistry since the first raindrop collected the first mineral from the first bare rock. And it would continue doing chemistry in increasing complexity and specificity until something arose that could do chemistry with direction, with memory, with the ability to copy itself. But that moment had not yet come, for now there was only the ocean, moving in its deep currents, accumulating in its chemistry, cooling toward the stability that would eventually allow something entirely new to emerge. Part 12, the colors of the ancient sky. Imagine standing on the shore of the early ocean. It is not possible. The atmosphere would kill you in minutes. But imagine it as an exercise in picturing a world utterly unlike the one you know, and yet made of the same elements, following the same laws, turning under the same sun. The ground beneath your feet is dark basalt, dense and fine-grained, still warm from the geothermal heat below. It is wet, not with rain at this moment, but with the evaporating remnants of the last downpour, which might have been an hour ago or yesterday. The surface is irregular, unsmoothed by any erosion except the direct action of water and wind, sharp-edged where it has fractured, glassy where it cooled rapidly. There are cracks running through it, some thin as paper, some wide enough to show the orange glow of lava far below. The ocean stretches away from you in all directions. It is dark, not blue, but a deep grey-green, the color of old oxidizing metal, turbid with suspended particles. Waves move across it, not gentle swells, but short, choppy waves, driven by a wind that moves in irregular patterns across an atmosphere with different pressure dynamics than you are accustomed to. The smell, if you could smell it, would be sulfurous, acidic, metallic. The sky above is not blue. It is a diffuse orange-brown near the horizon, shifting toward a darker, more reddish tone overhead, where the thicker carbon dioxide layer absorbs certain wavelengths of light. The sun, visible through this haze, is smaller and paler than you are used to, its light filtered through an atmosphere that scatters it differently. It gives the world a dim, orange-tinted illumination, not the warm gold of a sunset, but a permanent, neutral dimness, like the light inside a cloud. Clouds move overhead, dense and layered. They are not the delicate, varied clouds of the modern atmosphere, cumulonimbus and cirrus and stratus in their many forms. They are a more undifferentiated mass, thick with water, vapor and sulfur compounds, capable of producing heavy rain at almost any moment. When lightning occurs, and it occurs often, it moves through this thick atmosphere with a character different from the sharp, instantaneous lightning of a clear storm. It is more diffuse, more persistent, a glow that spreads through the cloud layer rather than a single bright bolt. At the horizon, the silhouette of a volcanic island breaks the flat line of the sea. It is not dramatic, just a low, dark shape trailing a thin plume of grey smoke that the wind bends quickly sideways. Steam rises from the shore where the lava meets the water, a constant hissing white column that joins the general overcast. Nothing moves on the shore. No birds wheel above the ocean. No crabs pick through the debris at the tide line. No insects move through the air. The tide line itself has no debris in the biological sense. No shells, no seaweed, no dried and tangled organic material. Just a line of minerals, crystallized salts, dark sediment, the chemical residue of the ocean's constant evaporation and refilling. The silence is not absolute. The wind makes sound. The waves make sound. The distant volcano makes a low, intermittent sound that carries across the water. But there is no biological sound, no call, no rustling, no breath other than the wind. The world is alive with physics and chemistry, but not yet with biology. And the difference between these two kinds of aliveness is exactly the difference between that world and this one. You stand on the shore of the early Earth, in this imagining, and what you feel is not desolation exactly. Desolation implies the absence of something that should be there. But this world is not missing anything. It is complete in itself at this stage of its development, doing what it needs to do in order to become what it will become. It is not a world waiting to be rescued by life. It is a world proceeding through its own processes at its own pace, indifferent to any quality we might assign it. And in that indifference, there is something almost peaceful. The ocean moves, the wind blows, the chemistry proceeds, the planet turns. Above it, the pale sun tracks its arc through the orange sky, and when it sets, the stars emerge, uncountable, in a sky with no light pollution, no cities, no fires. Just the galaxy spread overhead, and beneath it, a small, dark planet with a warm ocean turning slowly toward its next morning. Part 13. The late Hadean Ocean at rest. By the time the heavy bombardment had slowed to its lower, more occasional rate, the ocean had achieved a kind of equilibrium. Not a static equilibrium. Nothing about the early ocean was static, but a dynamic equilibrium in which the rates of input and output for the major chemical components were roughly balanced, in which the temperature of the surface was relatively stable, in which the major currents followed predictable patterns around the globe. The ocean covered most of the surface of the planet. The proto-continents that had begun to form were still small, still low, still frequently submerged or worn down by erosion. From space, the planet looked almost entirely blue-grey, the colour of a cold metal sphere wrapped in brown clouds. At the surface, in the well-lit zone where sunlight penetrated, the water was warmer, slightly less dense, moving in broad sheets, driven by wind and Coriolis forces. Below this surface layer, the water was colder and denser, sinking slowly toward the deep ocean in the polar regions, and rising slowly in the equatorial regions, where the surface water was heated and became lighter. This thermohaline circulation, as oceanographers call it, was already operating in some form in the ancient ocean. In the deep ocean, below the reach of sunlight, in the perpetual cold and darkness of the abyssal plain, the water moved slowly. Sediment settled onto the seafloor in a constant, gentle rain, particle by particle, layer by thin layer. Minerals precipitated from the water and joined the sediment. The hydrothermal vents emitted their plumes of warm, mineral-rich water that spread horizontally through the deep ocean before being absorbed back into the general circulation. The seafloor was dark. Not pitch black, because the hydrothermal vents emitted faint light, a dim glow from the heat of the water they expelled, but dark enough that any visual sense, had any visual sense existed to perceive it, would have found almost nothing to register. The darkness of the deep ocean floor in the early Archean was a darkness of a completeness very rarely experienced in the modern world, which has been so thoroughly lit by human civilization that true darkness has become difficult to find. In this darkness, the chemistry continued. The vent waters carried hydrogen sulfide and methane and carbon dioxide and hydrogen. And these chemicals mixed with the ambient ocean water and reacted. Iron sulfide minerals formed in the walls of the vent chimneys, creating porous structures riddled with tiny chambers. In these chambers, temperature gradients and pH gradients and chemical gradients concentrated the reactions, driving them toward particular products. The same physical constraints that would later make these environments attractive as potential birthplaces of life were already creating conditions of chemical specificity. Not life, not yet, but chemistry that had the quality of direction, that proceeded toward particular products rather than random ones, that generated complexity from simplicity in ways that would, much later, to be repurposed by the first living systems. The ocean floor in the late Hadean and early Archean was a place of slow, patient, directed chemistry. The word directed here carries no implication of intention. It means only that the physical constraints of the environment channeled the chemistry towards certain products. The porous walls of the vent chimneys acted like tiny reaction vessels. The temperature gradients acted like tiny energy sources. The pH gradients acted like tiny pumps. And across the seafloor, in the vast darkness between the vents, sediment accumulated. Year by year, millennium by millennium, the sediment layers built up. Each layer captured a moment of chemical time, the particular mineral composition of the ocean water at that moment, the particular rate of volcanic outgassing, the particular chemistry of the atmosphere above. The seafloor was becoming a geological record. It was writing the history of the ocean and the atmosphere into the strata of its own sediment, a record that would persist in some cases for billions of years, waiting to be read by creatures who had not yet evolved the cellular machinery to exist. Part 14. the turning. The Earth turned. Through the Hadean, through the early Archean, through the long cooling and the bombardment and the formation of the ocean and the beginning of tectonic activity, the planet turned, one rotation every several hours at first, slowing as the moon's tidal drag dissipated the angular momentum of the system. The day lengthened slowly, imperceptibly from any perspective that could register the change. But over hundreds of millions of years, the day grew from 6 hours to 10 hours to 16 hours. The lengthening of the day changed the patterns of weather, the distribution of heat across the surface, the dynamics of the ocean currents. Each incremental change was too small to cause disruption, but the cumulative effect over geological time was a world with a different daily rhythm, a different distribution of sunlight, a different character to its seasons. The seasons themselves were different in the early Earth. The axial tilt, which gives the modern Earth its seasons, was already present, but the moon's stabilizing influence was still being established. Without the moon, the axial tilt of the Earth might have varied chaotically, sometimes pointing the pole directly at the sun and sometimes lying nearly flat. With the moon, the tilt was stabilized within a range of roughly 20 to 25 degrees, creating the regular, predictable seasons that would later prove so important for the development of life. The moon was still close in those early days, much closer than it is now, only perhaps 10 Earth radii in the first million years after its formation. At that distance, it would have appeared in the sky perhaps 10 to 20 times larger than it appears today. Its tidal influence was proportionally stronger, raising tides in the early ocean that were far larger than the modern tide, creating intertidal zones of great extent, where the ocean retreated and advanced with dramatic regularity. These tidal zones, where land and sea alternated with the rhythm of the moon's pull, would later become among the most biologically productive environments on Earth. But in the pre-biological world, they were simply zones of unusual chemical activity, where the alternating exposure to air and water, to drying and re-wetting, created conditions that concentrated the organic compounds dissolving in the ocean water. The planet turned, and as it turned, each face was presented to the sun in sequence. The hemisphere facing the sun warmed, the hemisphere facing away cooled. Winds moved from high pressure to low pressure, from warm to cool, in patterns that circled the globe in great loops. The ocean surface was stirred by these winds, mixed, aerated at the surface, warmed in the equatorial band, and cooled toward the poles. The rhythm of day and night on the early Earth was not the rhythm we know. The hours were different. The light was different, filtered through that orange-brown atmosphere. The temperature swing between day and night was more pronounced because there were no forests to moderate it, no great mass of vegetation to absorb heat during the day and release it at night. But the rhythm was there. A turning, a warming, a cooling, a turning again. The most fundamental cycle of the planet, the alternation of day and night, was already operating in these earliest ages. It was older than any ocean current, older than any tectonic plate, older than the magnetic field. It was among the first consequences of the planet's formation, the simple fact of a sphere rotating on its axis in the light of a star. This rhythm would later become the heartbeat of the biosphere, entrained into the biology of every living thing that would ever exist. Circadian rhythms, seasonal cycles, the annual migration of birds and the flowering of plants, all of it would trace back to this most fundamental cycle. But in the Hadean, it was simply a fact of physics. The planet turned, The sun rose over one horizon and set at another. The temperature climbed and fell. And with each turning, the chemistry continued, and the geology continued, and the slow, patient preparation of a world for life proceeded one moment at a time across the silence of deep time. Closing. The long patience. This is where section 1 ends. Not with a dramatic event, not with a transformation, not with the beginning of anything that would be recognizable as a change in direction, just with the world as it was in the late Hadean and earliest Archean in its first equilibrium. A world of ocean and bare rock and orange sky and patient chemistry. A world heated from below and cooled from above, turned by its own momentum and steadied by its moon. A world whose geology was beginning to organize itself into the patterns that would persist in changed form through all the billions of years that followed. The ocean is dark and mineral-rich and acidic. The atmosphere is thick and poisonous and orange. The crust is thin and constantly recycled by the tectonic forces beneath it. The magnetic field wraps the planet in an invisible protection. The hydrothermal vents on the seafloor emit their plumes of warm, chemical-rich water into the cold darkness. The chemistry is accumulating, very slowly, in ways that will not produce their consequences for hundreds of millions of years. The ocean is becoming more complex. Organic molecules are forming in the ultraviolet light, at the surface, and in the heat of the vents below. They are dissolving, reacting, breaking down, and reforming. The ocean is doing what chemistry does. Given time and energy and a liquid medium, the planet turns. The sun rises over the dark ocean. Its light, orange and dim, falls on a surface with no life to receive it, no eye to see it, no organism to harvest its energy. It warms the surface water by a fraction of a degree. And then the planet turns again, and the sun sets, and the surface cools, and the night comes over the early Earth, a long, starlit night over an ocean that moves in its slow currents without making a sound that any ear would recognize. This is the silence before life. It is not an empty silence. It is a silence full of process, full of chemistry, full of geology doing its patient work. It is the silence of a world that has not yet been complicated by the extraordinary elaboration of matter that life represents. It is the silence of deep time, which is not like any other silence. It is the silence of billions of years of turning and cooling and reacting and settling. A silence so deep and so long that it becomes, in its own way, a kind of presence. The Earth is 4.5 billion years old. In the very beginning, it was this ocean, this rock, this orange sky, this patient chemistry. Everything that would ever live, every forest, every ocean filled with fish, every sky filled with birds, every civilization, every thought, every word ever written, all of it waited in potential in the chemistry of the early ocean. Not yet assembled, not yet possible, but waiting in the way that all future states wait in the present, implicit in the current conditions, reachable through the patient application of time and process. The planet turns, the ocean moves. The chemistry continues, and the long silence holds, patient and complete, over a world that is still, in every sense, becoming. Part 15. The chemistry of rock. There is a particular kind of rock called banded iron formation. and it is among the most beautiful things the early Earth produced. It forms in layers, alternating bands of dark, iron-rich minerals and lighter, silica-rich minerals, each band only millimeters thick. Hundreds of layers stacked one atop the other in formations that can be thousands of meters deep. These formations are found on every continent, in the oldest parts of the continental crust, wherever the ancient Archean rock has survived. They are the primary source of iron ore that humans have mined throughout history, the raw material of steel of the industrial world. The skyscrapers and the ships and the bridges were all, in some sense, built from the chemistry of the early ocean. But in the early ocean, banded iron formations were simply a geological process. Iron dissolved in the ocean water, released from the seafloor by hydrothermal vents and by the weathering of the volcanic crust. In the absence of oxygen, iron dissolved easily in water, remaining in solution as long as the chemical conditions permitted. When the water conditions changed slightly, when the chemistry shifted in ways driven by seasonal variations or volcanic events, or changes in the circulation patterns of the deep ocean, the iron precipitated out of solution, forming iron-rich minerals that settled slowly to the seafloor. Between these iron-rich layers, silica from the ocean water and from the shells of silica-secreting organisms, or in the pre-biological ocean, from the direct precipitation of dissolved silica, settled in the lighter bands. The alternation of iron-rich and silica-rich layers recorded the fluctuating chemistry of the ocean in geological time, each pair of bands representing perhaps a year, perhaps a century, depending on the rate of deposition. These rocks are a diary written in minerals. They tell the story of an ocean chemistry that fluctuated with the seasons, with volcanic episodes, with changes in the circulation that brought iron-rich deep water to the surface or drove it back to the depths. They record, in the subtle variations of their chemistry, the history of the early ocean's encounter with the first oxygen produced by the first photosynthetic organisms, though that story belongs to a later chapter. In the purely pre-biological ocean, before any oxygen existed, the banded iron formations record only the inorganic chemistry of a world still sorting itself out. The iron dissolved and precipitated, leaving its striped record in the rock of the seafloor, unconcerned with any future significance. Other minerals were forming in the early ocean sediments. Cherts, composed of fine-grained silica, formed in the still water of the deep ocean where silica had concentrated. Carbonates formed where the ocean chemistry allowed calcium and magnesium to combine with the abundant carbon dioxide dissolved in the water. Each mineral type carried information about the conditions under which it had formed: the temperature, the pH, the concentrations of particular dissolved elements, the rate of input from rivers and volcanoes. The early ocean was a chemical system of extraordinary complexity, even before the advent of life. Dozens of elements in solution, reacting with one another, precipitating onto the sea floor, being recycled by the hydrothermal vents, carried by currents from one part of the ocean to another. The steady state of this chemistry was not fixed. It shifted in response to changes in volcanic activity, in the rate of seafloor spreading, in the composition of the atmosphere. But it was organized. Not in the sense of having an organizer, but in the sense of having reached a configuration that was self-reinforcing, a set of chemical cycles that tended to return to roughly similar conditions after being perturbed. The chemistry of the early ocean had, in this sense, a kind of stability that was itself a preparation for the much more elaborate chemical stability that life would eventually introduce. Life, when it arrived, did not create chemical organization from nothing. It inherited a chemical world already organized by purely inorganic processes, and it added to that organization the extraordinary specificity and efficiency of biochemistry. But the foundation was already there. The rock was writing it down. Part 16. The atmosphere breathes. The atmosphere of the early Earth was not fixed. It changed slowly, on timescales of millions to hundreds of millions of years, driven by the volcanic outgassing of the interior and by the gradual removal of gases through chemical reactions with rock and ocean. The balance between these two processes determined the composition of the atmosphere at any given moment, and that composition, in turn, determined the temperature, the chemistry of the ocean surface, and the character of the weather. Volcanic outgassing in the early Earth released primarily water vapor, carbon dioxide, nitrogen, and sulfur dioxide, with smaller amounts of hydrogen, sulfide, methane, and other gases. Most of the water vapor condensed and fell as rain, joining the ocean. The sulfur dioxide dissolved in rainwater and reacted with rock surfaces depositing sulfate minerals. Carbon dioxide was more persistent. It dissolved in the ocean but also remained in the atmosphere in significant quantities, creating the greenhouse effect that kept the surface warm enough for liquid water despite the fainter young sun. Nitrogen, which does not dissolve easily in water and does not react readily with most minerals, accumulated in the atmosphere over time. Being neither added rapidly nor removed efficiently, its proportion in the atmosphere grew slowly as the more reactive gases were processed out. Nitrogen now makes up roughly 78% of the modern atmosphere, and that dominance began in these early ages. When nitrogen accumulated by default, the residual gas remaining after the more reactive components had been cycled through the geological and, later, the biological systems of the planet. The atmosphere had weight. It pressed down on the ocean surface with a pressure that would have been crushing by modern standards, much higher than the current atmospheric pressure at sea level. Because the total mass of gases in the early atmosphere was greater, with more carbon dioxide and sulfur compounds than exist in the modern air. This higher pressure affected the chemistry of the ocean. Gases dissolve more readily under higher pressure, so the early ocean contained more dissolved gases than the modern ocean does at equivalent temperatures. The carbon dioxide dissolved in the ocean created carbonic acid, contributing to the ocean's acidity. The dissolved hydrogen, sulfide, and methane contributed to the chemical richness of the water. Wind patterns in the early atmosphere were determined by the same basic physics as today, the differential heating of the surface creating pressure gradients that drove air from high pressure to low pressure, modified by the Coriolis effect of the rotating planet. But the specific patterns were different. There was no land in the northern hemisphere, or very little, and so the large-scale circulation patterns that are disrupted by continental land masses in the modern atmosphere moved more freely in larger, more regular loops. Storms on the early Earth were large and persistent. The atmosphere, holding more energy from the stronger greenhouse effect, was capable of producing storm systems of considerable intensity. Cyclonic systems, fed by the warm ocean surface and the unstable atmospheric conditions, circled the globe on tracks that would have no modern equivalent. Lightning was frequent, both in the storm systems and in the volcanic plumes that rose from the active seafloor spreading centers and volcanic islands. Each lightning bolt was a brief, intense chemical event. The electrical discharge moved through the atmosphere at temperatures of tens of thousands of degrees, hot enough to break apart even the most stable molecular bonds and allow elements that would not normally react to combine. The products of these lightning-driven reactions were varied and chemically interesting, including compounds that would later become important components of biological chemistry. The atmosphere was, in this sense, a reactor. Not a purposeful reactor, not one designed to produce any particular output, but a system in which energy, in the form of lightning and ultraviolet radiation from the sun, was constantly being used to drive chemical reactions, to push matter into higher energy, more complex configurations. Most of these configurations were unstable and quickly broke down back to simpler compounds. But some were more stable, and some of those stable compounds accumulated in the ocean and on rock surfaces. The atmosphere was contributing to the chemistry of the world. Not with any intention, not with any direction, but as a simple consequence of the fact that energy flowing through a chemical system produces reactions, and reactions produce product, and some products are more stable than others. The early atmosphere, full of energy and reactive chemicals, was doing what reactive chemicals do in the presence of energy. It was making things. Slowly, over hundreds of millions of years, the atmosphere evolved. Carbon dioxide was drawn down by weathering reactions and by dissolution in the ocean. Sulfur dioxide was removed by reaction with rock surfaces. Methane was destroyed by ultraviolet radiation and by reaction with the small amounts of oxidizing compounds that formed from the photolysis of water vapor at the top of the atmosphere. The atmosphere became, very gradually, less chemically reactive, more stable, more dominated by the inert nitrogen that had accumulated by default. This was not yet the air anyone could breathe. It had no oxygen. It was still toxic by the standards of any modern organism. But it was a different kind of toxic than the early Hadean atmosphere, a more quiescent, less actively poisonous mixture that was, in a relative sense, becoming more moderate. The atmosphere was settling, finding a less extreme version of itself, trending very slowly toward the kind of stability that would eventually make it possible for the chemistry of life to operate within it. But it was not there yet. The air above the early ocean, in the late Hadean and early Archean, was still brown and still carried enough sulfur compounds to be acrid, still contained enough carbon dioxide to be narcotic at the concentrations present, still lacked any trace of the oxygen that we now consider simply a fact of the air. It was breathable only in the sense that it had pressure, only in the sense that it was a gas through which sound could travel and in which weather could occur. In the sense that matters to living things, it was nothing like air. It was something else, something without a common name, because nothing with a common frame of reference has ever breathed it. And yet, it was doing its work, carrying heat, distributing water, reacting with rock, absorbing and releasing energy. The atmosphere, however toxic, was a working component of the planetary system, playing its part in the great, slow cycles of geology that were preparing the world for what would eventually come. Part 17, Ending the Beginning. Everything described in this section, the formation of the Earth, the differentiation of the interior, the great impact and the formation of the Moon, the cooling of the surface, the coming of the rain, the filling of the ocean, the beginning of tectonic activity, the accumulation of organic chemistry in the ocean and the atmosphere, all of it happened before life. All of it. Before the first cell. Before the first self-replicating molecule. Before the first metabolic pathway. Before anything that we would recognize as alive had assembled itself from the chemistry of the ancient ocean. This period lasted roughly 500 million years, perhaps more. In those 500 million years, the planet completed its basic architecture. The core organized itself. The mantle established its convection patterns. The crust differentiated into oceanic and protocontinental rock. The ocean filled. The atmosphere evolved. The hydrological cycle began. The magnetic field stabilized. All of this was preparation, in the sense that it made the subsequent appearance of life possible, though not inevitable. Nothing about the Hadean Earth guaranteed that life would ever appear. The chemistry was assembling the components, but assembly of components does not guarantee assembly of a system. Many planets have the components without having the system. Mars had liquid water very early in its history. It had volcanic activity and a magnetic field and an atmosphere. It had, probably, much of the chemistry that the early Earth had. And yet Mars is, as far as we know, a dead world. The difference between Mars and Earth is not entirely understood. It may lie in the sustained presence of liquid water on Earth, which Mars lost relatively early as its magnetic field declined and its atmosphere was stripped away by solar wind. It may lie in the plate tectonics that recycled Earth's crust and maintained the chemical cycles that keep life's elements in circulation. It may lie in chance, in the random outcome of a chemical system that had many possible trajectories and took one rather than another. What is known is that on Earth, the chemistry did eventually produce life. But that is the next chapter. This chapter ends here, in the late Hadean, with the ocean full and the crust thickening and the atmosphere slowly evolving and the chemistry of the ocean growing more complex. Nothing has happened yet in the biological sense. The world is still a world of pure geology and chemistry, of rock and water and air interacting according to physics without any biology to complicate the picture. And in that simplicity, there is a kind of completeness. The pre-biological world was not a failed world. It was not a world that had not yet succeeded in doing what it was supposed to do. It was doing exactly what it was doing, which was being a planet, cycling its chemistry, maintaining its temperature, organizing its geology, proceeding through the processes that physics and chemistry required of it. It had no goal. It had no direction. It had only the laws of nature acting on the particular arrangement of matter that happened to exist at this location in the solar system. And from those laws acting on that matter over those hundreds of millions of years came the world that was ready. Not ready in any intentional sense, but ready in the sense that the conditions were present. The chemicals were in the ocean. The energy gradients were available at the hydrothermal vents. The protected environments existed in the porous rock and the sheltered pools. Everything was in place. The ocean moved in its currents, slow and dark and mineral-rich. The atmosphere stirred above it, orange, brown, and thick with carbon dioxide. The crust shifted beneath it, thin and restless, driven by the heat of the interior. The moon pulled at the tides. The sun moved across the sky. The planet breathed in the only sense it could breathe, the slow exchange of gases between rock and ocean and atmosphere, the long inorganic respiration of a world that had not yet learned the biological version. And in the chemistry of the ocean, in the mineral-rich water of the hydrothermal vents, in the concentrated pools of organic molecules that had accumulated over millions of years of patient chemistry, something was very nearly ready to happen. Not yet, but nearly. The long silence of the pre-biological Earth stretched on, as it had stretched on for 500 million years, but it stretched now over a world that was qualitatively different from the molten chaos of its beginning. Quieter, deeper, more organized, more chemically rich. A world that had learned, through 500 million years of geological process, to hold itself together, to maintain its ocean and its atmosphere, to cycle its chemistry, to sustain, against the void of space, the conditions necessary for something extraordinary. The planet turned, the ocean moved, the chemistry waited, and the long silence of the world before life held its last deep breath.